Hello, welcome to this session on Visums ABM. As you already know, if you joined me last week, my name is Martin. Today we will dive deeper into the mechanisms of Visums ABM, focusing on the underlying theory, workflow, and its stability. We start with a comparison of an ABM with a four-step model. In a four-step model, the mobility is defined per person group, while in an ABM, we analyze the mobility of each individual person. In a four-step model, we calculate probabilities, and the result consists of fractions of trips. So, for example, only 30% use car and 70% use public transport. In an ABM, there's always a concrete decision. The decisions are simulated, and one person decides for 100% for this or for that alternative. A four-step model is trip-based, what means, among others, that constant trip rates are applied, while the ABM acts on complete activity chains. The result structure in a four-step model is a set of matrices. For example, as here, one matrix per mode. The result structure of an ABM is a daily plan. One daily plan for each individual person. And this daily plan includes a lot of detailed information about the activity chain, about the start of each activity, start time of each trip, end time of a trip, duration of an activity, duration of a trip, and so forth and so forth. The ABM procedure in Visum is called ABM nested demand. This procedure is a fully integrated process. That means especially no scripts is required. As you see here, there are proper dialogues, and it's quite easy to use. You can define here tour groups based on person attributes, household attributes in a quite smooth way. You can define the utility quite simply. The methodology is very closely related to a four-step model. You could call that a disaggregated nested tour-based model. It's a proper probabilistic model, as you see here, completely nested. And since the methodology is so close to the four-step methodology, also parameters can be transferred from the old models to this ABM, and also the data can mostly used, and there's only a little additional data necessary. What you see here is the supported workflow of our ABM. As in a four-step model, you start with a certain population, and then the model decides for time, destination, and mode. By the way, in any sequence. In an ABM, this population is a synthetic population. That means it consists of concrete persons with certain characteristics and with a daily plan skeleton. Skeleton means here it's a complete daily plan, just without those items which should be chosen later by the model. That means without times, start times, end times, without destinations, and without modes. Okay, the question is, how do we get these persons, this synthetic population? We get that from a household survey, from a household interview survey. Actually, we clone existing persons from a certain survey and put them into our model. Okay, how does that work? How do we create a synthetic population based on a sample from a household interview survey? So we start with this sample. We start with concrete persons surveyed in a household interview survey. All these persons have certain characteristics and they have a complete daily plan. Actually, we use only the skeleton of these plans. On the other side, on the model side, we have a model area, and the model area is distributed into something like, say, microzones. So typically in a macroscopic model, you use zones. Here we have something smaller. It could be buildings or a set of buildings, whatever. We just call them here microzones. Okay, and now these microzones do have some certain marginal distributions. We know about this one first microzone. There live 32 full-time employees and 11 part-time employees and 5 young adults, 7 pupils and whatever. And now we need to clone, to duplicate the original sample persons to this model area, to the microzones, in a way that these marginal distributions are matched. And this is done typically by a population synthesizer, like, for example, Population Sim. That's a software that produces such synthetic population. Okay, and what do we now? We add also the daily plan skeleton to the persons. So we take the original surveyed daily plan and add them to the corresponding person. So again, I show that here we don't just distribute or duplicate or clone the sample persons, but these sample persons also take with them their daily plan. Now let's have a look into the mechanism, how the ABM works, how the choice works. Here with an example, with a quite simple example about a mode choice from home to work and back home. You see the schedule is already somehow filled. We know the home location, we know the work location, we know the start time of work, the duration of work, and what we want to know is the mode. So the mode should be chosen here. And how does it work? To decide for the mode, we need the general costs. We need to calculate the costs for a trip from home to work. And we do that in our ABM based on the shortest path. So this is not anymore zone-based as typical 4-step models are, but it is somehow spatially microscopic. And we use the shortest path in the network. And of course, for each mode, we calculate that separately. Okay, but we don't take any shortest path because we know that the work starts at 9 o'clock. And that means also the trip will happen before 9 o'clock, somewhere, for example, in the time period from 8 to 9. And that's why we calculate the shortest path in this time. And maybe some roads are very occupied, and so there's another path, the shortest path, than in other situations or in other time periods. And there's something else what we already know. We know the duration of the work activity. In this case, a bit more than 8 hours, and that means the trip back will happen after 5 p.m. And we already consider also this trip. So the utility for the mode choice, for the trip to the workplace, is composed by both trips, the trip there and the trip back, and each trip in the correct time period. And that is quite important if you imagine a situation where there is in the morning a very good public transport connection from home to work. Say there is a bus a quite fast bus, but in the evening when you go back home, there's possibly no bus at all, no public transport possibility. And that means you would already in the morning choose something else than public transport, because you know for the trip back there won't be any such possibility. And you would possibly choose then the car also for the trip there. In a typical four-step model, you would choose for the trip there a bus, and for the trip back then a car, what is obviously not very realistic. Now I come to a certain detail of the shortest path, and it is about the public transport shortest path. As said before, we need to calculate the costs for a trip per mode, also for the public transport mode, and we do that based on the shortest paths. The shortest path starts here at the blue triangle and goes to the first stop. This is a walk path or a walk path leg. You see here. And then it goes from this stop to the end stop via a matrix. So this is a stop area matrix, and we choose a certain path through this matrix, so from one stop area to another stop area. And then the last part of the trip is again in the network, in the work network, from the stop to the final destination, to the final location. A good thing here is that you don't need any public transport connectors, because the access and the egress from and to the stops is done in the walk network. So if you change, for example, the position of one stop area, then the model reacts automatically, and there's no need to adapt any connectors or so. Let's come now to a topic that is quite unknown by traditional modelers. It's about stability. Every traditional four-step model is completely stable in some sense, but an ABM is not. A normal ABM is based on Monte Carlo simulations. That means somehow that all decisions are based on random numbers that are generated by a random number generator. So in each iteration or in a scenario, there are thousands of new simulations. For every person, every decision is simulated. And since these random numbers are not somehow kept stable or fixed, there's always a new decision. And on micro level, you don't see any stability. Every individual person may decide now this and later that, although nothing has changed actually, just because of this random characteristic of the whole process. And then it may be a problem to separate the reaction, the systematic reaction of the model on some measures from white noise. You cannot see sometimes the systematic changes because there's so much white noise. The good news is that Visum's ABM is stable. And I will show you in the next slides why. We will first have a look into the typical simulation of a discrete choice. In all these models, there is at any point a logit model, and the logit model is fed with certain travel times, wait times, and so on. And from that, we derive probabilities for each alternative, in this case, for each mode that can be chosen. And having these probabilities, we run a Monte Carlo simulation. That means we choose a random number, in this case 0.42, what means then that we will choose the bike. To understand what we do differently from other ABMs, we need a bit different look on the situation. So actually, the discrete choice theory of logit models is based on individual preferences and not only on the systematic utility. As you see here in a choice situation, the utility of each alternative consists of two parts. One part is a systematic utility, something like travel time, waiting time, and so on. But there's also another part, and that could be called individual preferences. In the formula, it is U is equal to V plus epsilon, and this epsilon is the individual preference. And this is different for each person. And it decides also which of these alternatives is chosen, because the sum of both parts make the final utility, and the alternative with the highest utility wins. So in this case, it would be bike. Now let's have a look what happens in a typical ABM simulation. There it is as if every person gets permanently new of these individual preferences, as if we would choose them again and again. So in iteration 1, we have a certain set of individual preferences, and in iteration 2, we have a completely different set, and that may cause a different decision. So in this case, the person would choose car, while the systematic utility did not change at all, but the individual preferences did. The difference to our ABM is that we keep these individual preferences constant. And that makes our ABM stable. All the preferences remain unchanged. They are chosen in the beginning of the process, and then they remain unchanged throughout the whole process. This does not mean that the choices are somehow fixed. If something changes, for example, as in this scenario, that means if the systematic utility changes, you see that here the car is much better than before, so the utility of the car is better, then also the choice may change. You see, the individual preferences are the same as before, but the systematic utility of car has improved. Together, in sum, the car utility is the highest one, and that's why we would choose here car. And this is completely okay. It improved, and therefore we may change to this alternative. With this method, we get a completely stable system. There's actually no random noise at all anymore in this system, in this choice process, and we can very well compare base cases with scenarios. And I will show you here what happens if we don't use this stability, if we run a conventional ABM and we run a scenario. So what you see here is the morning toll. So just assume that we introduce a certain toll for car use in the morning only, and then we count the number of more or less car users for each location. And you see in this conventional case, a lot changed here. So there are some red and some green triangles, what means in some cases there are less users. That's actually what is expected. I mean, we introduce a morning toll, we make car trips more expensive, and then some people should choose another mode. And that happens here. But also the opposite happens. Some people choose car, although the costs had increased. And that's a bit weird, isn't it? But this happens because all choices are somehow random. And all in all, if you have a look at the whole situation, maybe there is a certain trend towards less cars or less car use. But for any individual, you can't see a clear picture. And this is completely different if you use Visum's ABM. This is completely stable. And you see there are only red triangles, what is expected actually, because some of those users, some of the original car users change now to something else because car became a bit more expensive, and then they changed their mind or changed their decision and perhaps used public transport or bike or so. But only few of them. And all the rest keep their original decision.
Did you learn anything exciting in this session? Then join me once more on Wednesday to explore the dialogues of Visum's ABM procedure and dive into its parameterization.